Wait, what? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Thank you. everyone. My name is Stephanie. This is the Chem 2046 review. It goes from 10 to 12. So if you're not here for the review, I'm going to have to ask you to leave. But I think most of you are here for the review, if not all, I think all. So welcome. This review is about 30 questions long. I posted it on the UCF Study Union Google site. So this is the website where you can find it later. The answers are also on the back at the end because it's a multiple choice type test. But I'm going to go through it, how to solve all the problems. If you have questions that are problem specific, so based on the current problem we're going over, then feel free to raise your hand and ask those. If you have unrelated questions, please save those for the end. We're going to end about 10-15 minutes early, so around 11:45, 11:50. So that you have time to ask those last minute questions that I may have not gone over in the review, or also so you guys have a chance to take this survey. They have, I think, the survey is a sheet that looks something like this. So if you would please take the survey, either by using the QR code or going to that link, the Study Union survey link, that would be great. Also, we have a review right after this one for a different course, so we also want to have that 10-15 minutes to clean up and be on our way out afterwards. But as I said, the review is located on this, the Google sites for UCF Study Union. And yeah. Do you have any questions so far? Are we okay? Cool. Then we will begin. Oopsie. Okay. Also, this review is going to be live streamed and recorded. So if you want to see this later, the problems worked out again, you can go to the YouTube page for SARC and look for Chem 2046. And you can find that, see it again, if you'd like as well. So the Google site for UCF Study Union has the written review, and then the YouTube page for SARC has the video of the review, or will have. Okay, so the review is broken up by chapter. So I started with chapter 11. There's a few questions from here, and then we'll go through, I think it goes through chapter 18, not 19. So if you have questions on 19, please save those for the end. So first question is, which of the following has the lowest boiling point? And it gives us A, B, C, D, E choices. So the lowest boiling point is going to have the strongest intermolecular forces, or lowest boiling point. So that means the least amount of heat to break up those intermolecular forces. That's kind of what we're going for. So the least amount of heat would be really weak forces. They take the least amount of heat. So we're looking for weak forces. So if we go through our answer choices, we have NH3. So if we draw NH3, we draw the Lewis structure of NH3, we're going to have nitrogen with 3 hydrogens attached by single bonds, and that lone pair. This lone pair is going to make this orientation polar, because we don't have hydrogens on all 4 sides pulling with equal forces. So we have something that's polar. We also have nitrogen-hydrogen bonded together, so we have hydrogen bonding. So this is one of the strongest forms of intermolecular forces. So the strongest is probably not going to be the answer for lowest boiling point. That would look more toward the end of highest boiling point. So we'll go to the next one. We have CH3Cl. So we draw that one. We have carbon with 3 hydrogens bonded to a chlorine with its lone pairs. So the chlorine-carbon bond is a polar bond that makes this molecule polar. But it doesn't have any hydrogen bonding. So far B would have a lower boiling point than A, but maybe not the lowest. So we'll go to C. C is sodium chloride. Sodium is a metal. Chlorine is a nonmetal. So we have an ionic compound. Bless you. We have an ionic compound. So in ionic compounds are made of ions. So we have a cation from sodium, an ion from chlorine. These are ions, so they have really strong forces between them. They have a full positive, a full negative. In polar, we only have partial charges. So this is actually even stronger than that ammonia in A. So far, B is better from A, B, and C. Then we go to D. D has CO2. We draw CO2. When we draw CO2, we'll end up getting carbon with 2 double bonds to our oxygens, because this will give carbon with 0 formal charge and oxygen each with 0 formal charge. So they're better structure. Because we have oxygen on both sides, they're both double bonded to carbon. Even though carbon-oxygen would make a polar bond, these polar bonds are pulling with equal and opposite forces. So this molecule is nonpolar because of that. So to be polar, we need an overall dipole moment. We have one dipole moment with this polar bond, another one here, but they cancel out, so we don't have a net dipole moment. And we also need those polar bonds, which are present, but they get canceled out. So that one's nonpolar. So that one now is our new least or weakest interaction between CO2. So that one will have our lowest boiling point so far. Then we look at E. E is a bunch of hydrocarbons. So that's also going to have nonpolar interactions, but how it's written is in a long chain form. So the longer the chain, the more surface area this molecule is going to have. So the more chances and more opportunities it has to interact with more molecules, the more dispersion forces you're going to have. And although dispersion is the weakest force you can have, when you have a lot of weak forces added together, it's going to create a stronger interaction than a small amount of weak forces that you'll see in CO2. So when we're looking for the one with the lowest boiling point, it's going to be the one with the weakest intermolecular forces and the smallest surface area. So for 1, we're looking at D. Okay. And then 2, we want to know which one will have the lowest, or for 1, do we have any questions on 1? Yeah. C is only made up of ions, so we only have ion-ion interaction. If you have ion-dipole interaction, you're going to have something that's polar and an ion interacting together. So like sodium chloride and water would have ion-dipole interactions. If you're just looking at one substance, you're not usually going to find an ion-dipole interaction because you can't really have something that's ionic and polar. Usually it's a spectrum of nonpolar to polar to ionic. But good question. Other questions on number 1, intermolecular forces and boiling point? We're okay. So number 2, we're looking at which one will have the lowest vapor pressure. So vapor pressure, we're usually looking at a liquid with its vapor above it in a closed container. So the vapor pressure is going to come from how much vapor we have above our liquid. So the substance with the really weak intermolecular forces is more likely going to vaporize. So really weak forces have a high vapor pressure. So we want to look for the lowest vapor pressure, so we're looking for strong intermolecular forces. Okay. So A, we have CH3F. So we have a carbon with 3 hydrogens and a fluorine. So this gives us a polar molecule because the carbon-fluorine bond is polar and it has a net dipole moment. So we have a polar molecule that's pretty strong compared to something that's nonpolar, but maybe not the strongest. So then we'll look at B. B is CH3OH. So that would be a carbon with 3 hydrogens bonded to an OH group. So it's going to get that bent shape. So that OH group is going to make things polar. We'll actually have 2 polar bonds. Or not polar, sorry. Drew my arrow wrong. Okay. So we'll have polar bonds. They're going to be pulled toward the oxygen, away from carbon, away from hydrogen. So this is a polar molecule because those dipole moments don't cancel out. We also have oxygen bounded to hydrogen, so we have hydrogen bonding. So that's even stronger than just regular dipole-dipole. So polar bonds mean, or polar molecule means we have dipole-dipole. If we have that OH or FH, NH, we have that hydrogen bonding. So B has hydrogen bonding, it's stronger than A, so far B is our better choice. But let's look at the other ones in case we have something better than B. So we'll look at C. C is CH3OCH3. So this one also has hydrogens and oxygens and carbons. So we have a C bonded to 3 H's, bonded to an oxygen, which is bonded to a C, which is bonded to 3 H's. Okay. This one is also polar. I drew it linear, but it's really going to be a bent shape. We don't have an oxygen bonded directly to a hydrogen, so we don't have hydrogen bonding. This one is just polar. It just has dipole-dipole interactions. So far, B is our better answer because we have hydrogen bonding with that. Then if we look at D and E, those are just hydrocarbons, so just carbon-hydrogen, carbon-hydrogen. Those are going to be nonpolar molecules. The longer chain is going to have more interactions, so it'll have a lower vapor pressure than the shorter chain, but it's nothing compared to, or not nearly as low compared to our polar and our hydrogen bonding. So because B had that hydrogen bonding, A and C were just polar, B is going to be the one with the lowest vapor pressure, so the one with the least vapor because they have the strongest intermolecular forces. Okay. Do we have questions on vapor pressure or intermolecular forces? Are we okay? There's a question, yeah. Chain lengths. Okay, so the longer your hydrocarbon chain is, the more surface area there is to interact with other molecules in a solution or in a vapor. So if it has more opportunities to interact, it has more opportunities to make dispersion forces between them. And the more dispersion forces you have, the better they're going to interact and kind of make a bond together, or more likely to interact together. Because although we have dispersion in both D and E, we have more dispersion in E because of that surface area. And if we have more of those weak interactions, it makes it a little bit stronger than just less of those weak interactions. So it's kind of like trying to tear one sheet of paper versus trying to tear like 5 layers of paper. One's going to be a little bit harder than the other, although like paper isn't that hard to shred compared to like plastic or something. Okay. Other questions? Are we okay so far? We're good? Cool, cool. Okay. Nope, cool. Number 3, we have our phase diagram. So number 3 says if CO2, so this is a phase diagram for carbon dioxide, and we're going to use it for number 3. It says if CO2 at negative 100 degrees, so this is negative 50, so negative 100 is probably around here somewhere, roughly. Negative 120 ATM, 20 ATM is probably over here, so we're probably looking somewhere in here, is heated to negative 40 degrees Celsius at constant pressure. So we're going to keep our pressure the same, go to negative 40. probably around here. Yeah, somewhere in here. What phase change will occur? So with this phase diagram, we want to remember what our different areas of our phase diagram are. So from very low temperature, very low pressure, we're going to have, or even high pressure, with just low temperature in general, our molecules aren't moving around as fast. They're more condensed, so we're going to have solid over here. At higher temperature, we're going to have our liquid, and then our gas is going to be over there. So if we're going from negative 100 to negative 40 degrees, staying at 20 atm, we're going from solid to liquid. And if we go from solid to liquid, that phase change is going to be fusion. Sublimation was, does anyone remember what the phase change for sublimation was? Solid to gas, kind of like dry ice, which carbon dioxide at solid would be dry ice. So from solid to gas would be sublimation. Condensation would be what phase change? Condensation. Gas to liquid, and then vaporization backwards, liquid to gas, yeah. And a phase change does occur, so something did happen. It was fusion. So we just have to remember where our states are in our phase diagram, and then what those phase changes will be. What's this point called when all of the kind of phases interact? Yeah, we have that triple point there. Triple point. And then what about that point where our liquid and gas kind of reach that equilibrium? This is the critical point, yeah. At the critical point, you'll have that supercritical fluid if you go above that temperature or above that pressure. So anything in this, well, not really that box. I think it's anything outside of it. But yeah, critical point. Okay. Do we have questions on phase diagrams? Yeah. Yeah, solid to liquid. So that's melting. Fusion's like a fancy way of saying melting. Melting. So fusion will be melting. Liquid to solid, they just use freezing. So there's no funny name for that. What about, so we have solid to gas is sublimation. What about gas to solid? Does anyone remember that one? Deposition. So just remembering those terms for this type of graph was good. So fusion, melting, we're good. Okay. Other questions on 3? Are you okay? Okay, cool. Okay, then we look at 4. Okay. Yes. It's on the UCF study in Google sites. If you try to search it on like if you Google it, it won't come up. It comes up as the SI Google site, so you kind of need the actual link. You can find the link also on the Facebook page for SARC. It's also here. You may have it if you want to look at it. Okay, so 4. We're looking at acetone. Let's maybe zoom in on this so you can see a little bit better. We have acetone, which is C3H6O. It has a melting point of negative 94.8 degrees Celsius and a normal boiling point of 56.1 degrees Celsius. And we want to figure out what the energy, how much energy is required to heat 29 grams of it from 0 degrees to 60 degrees. Okay, so with this, we're going to want to look at our heating curve. We're going to want to see what phase changes we're going through, if any, to see exactly what we're going to be calculating. So if we're looking at our heating curve, we're going to have our energy on our x-axis and our temperature on our y-axis. We're going to have that step graph. Remember that. So we have our solid, our liquid, our gas. We have, bless you, our fusion and our vaporization. At the point of solid to liquid, we're going to have fusion, so that's their melting point. So we have negative 94.8 at the melting. At our vaporization point from liquid to gas, we're going to have our boiling point, so that's 56.1. We're going from 0 degrees to 60, so we're going from 0, we'll be in liquid state, somewhere in liquid, and then we're going all the way to 60, which is above the boiling point. We're going to be going to gas state. So we're going to have liquid to boiling, a phase change from liquid to gas, and then going from the boiling point to our final temperature. So we'll have 3 steps in this problem, 3 different equations we're going to have to go through to do this. Okay. So we start at 0, we go to 60. So for our first one, we have a phase, we don't have a phase change. We have a change in temperature just in liquid state. So we're in liquid, we have a change in temperature, so we're going to use Q equals MC delta T. Their C is going to be for liquid. So C for liquid, we look at our constants, we have 125.5 joules per mole Kelvin. So when we calculate Q, Q is heat, M is mass in, actually it's going to be, are we going to use grams for this in mass with this Q equals MC delta T like usual? Yeah. We would think we would, but because our specific heat is in joules per mole Kelvin, we have to use moles to cancel out to get joules by itself, because our heat's going to be in joules at the end. Either joules or kilojoules. This constant has joules, and this constant has moles, so we have to use moles. Right now we're in, according to the problem, 29 grams. So we have to go from grams to moles. So we have to divide by our molar mass. So 1 mole, we have to calculate our molar mass. We have our molecule is C3H6O. So we have 16 from the oxygen, from 1 oxygen. We have about 1 from hydrogen and about 12 from carbon. So we're going to have 16 plus 6 plus 36, 40, 52, 58? Yes. So 58 grams, so 29 divided by 58 should be about a half. Yes, should be a half, so we get a half of a mole. We have to put a half mole in here, even though it's in our Q equals MC delta T, because of our constant, because that specific heat is in moles. That's why we're using moles. Yeah, usually you're given the constant in joules per gram, and it's usually degrees Celsius as well. So this constant is just a little bit different than what we're used to working with. So you have to pay attention to those units of your constants to give you a hint of what units you're going to use in your equation. Also, if you don't remember your equation that well, you can also look at your constant to kind of see what you need to do for that problem. So if I see constants like this, where I have like joules per mole Kelvin, I'm like, okay, I'm going to need moles, probably multiply that in, probably going to need temperature to kind of figure out what my joules would be, because I know joules is heat. So we put 0.5 in there, we put our constant in for our liquid, our 125.5, and then we need our change in temperature. If our change in temperature, or our temperature is in Celsius, and we need Kelvin because of our specific heat, do we have to convert if we're using delta T? Why? Yeah, so because we have Celsius and Kelvin, and we're only finding the change in the temperature, we can keep it in Celsius, because going up 1 degree Celsius is the same as going up 1 Kelvin. They have the same increments, but they just don't have the same starting point. So if you just have an equation that uses T or 1 over T or something like that, then you would need to convert, and there's no way around that. But because we have delta T, we're trying to find the change, so how many increments we went up or down. That's why we can keep it in Celsius to make numbers easier. But if all else fails, you can always convert if you don't remember that. But to make things easier, we're just going to keep it in Celsius because it'll be fine because we're looking for delta T. If we're looking for delta T, we want to only use temperatures that can be liquid. So we want to use our starting points. Delta is final minus initial, so our initial is 0. The final can only be our boiling point, because if we go past our boiling point, we're not a liquid anymore. And we're using a specific heat for liquid. So we have to go up to our boiling point, which is 56.1. So we have 56.1 minus 0. It's going to give us that 56.1. Because we have final minus initial, our final has to be boiling point, because above that, we're not a liquid anymore. This specific heat is for liquid. So if we multiply this out, I'm not sure. What do we get? Wait, can you repeat that, sorry? 0.3. Is this in joules or kilojoules? Joules. Let's see. Answer choices are in kilojoules, so we're going to convert. When we convert to kilojoules, we move the decimal place over 3. So 1, 2, 3. We could do that. If you want to do that, we can do that as well. If you change the temperature, you're adding 273 to both of them. And when you find the difference, it will be the same difference. So if you have 273 plus 56.1 minus 0 plus 273, you're going to get the same difference. But if you would like to do that, you may as well. But for this one, it won't matter because we're doing the difference. If we weren't doing the difference in temperature, then yes, definitely add 273. There's no way around that. And we'll round to 3 sig figs. So we'll have 3.52 kilojoules. So that's for the first step. That's going from our liquid at 0 to our boiling point. Now we have to do our second step, so liquid to boiling. Now we have to do a phase change from liquid to gas. So when we go to liquid to gas, we do a phase change. We're going to use our Q equals N delta H. Specifically, this is vape because we're going liquid to gas. MC delta H? Usually you don't have your C, your specific heat, with your delta H's because your specific heat is for a specific state of matter, so solid, liquid, gas, and your delta H is for changing states. So changing between solid and liquid and changing between liquid and gas. So that's why we have different equations. We have to do different steps for them. Because in our, when we change states, we're increasing energy, but we're not increasing temperature. We don't have a change in temperature. So if we try to use Q equals MC delta T for that, we're going to have a delta T of 0, we're going to have a Q of 0, but we end up having energy increase when we go from liquid to gas. So we can't use that one. So we have to use heat of vaporization. So heat of vape for this is given. It's 29.1 kilojoules per mole. So we have kilojoules per mole. So N is going to be moles, it's going to stay moles because our constant is kilojoules per mole. We solved for mole last time, it was the 0.5. And then we can put in our heat of vaporization, our 29.1. Mole, kilojoules per mole. So if we multiply that out, thank you. 14.5, is that in kilojoules or joules? This is in kilojoules because of the units given before. But that's only our second one. We have a third one. We have to go from our boiling point to our final temperature, which is at 60 degrees. So one more step. So for this one, we're in gas form now, so we have to use MC delta T. We have a change in temperature. We're only staying in gas form. So our C of our gas or our vapor is 75.0 joules per mole, or joules per mole Kelvin. Joules per mole Kelvin. Because MC delta T. So this one we have joules per mole Kelvin, so we're still going to use Kelvin Oh, not Kelvin. We're still going to use moles. We can also use Kelvin if we need to. But the change in temperature is going to cancel that out anyway. So for Q equals MC delta T, we're still going to use moles because our constant is in moles. Our C is going to be the one for vapor or gas, 75. And our delta T is going to be final minus initial. So our final is at 60 degrees, what we want to end up at. And our initial is the lowest temperature our gas can possibly be, and that's the boiling point. If you like to convert these to Kelvin first, you can always add 273 to both sides, or both of them. But they will cancel out when you subtract them. So if we multiply this out, what do we get? 0.25. Is this in joules or kilojoules? This is in joules. So we have to convert to kilojoules before we add. So we move it over 3 times. We get 0.146. We'll round to 3 sig figs. This is in kilojoules. Now we have all of our heats, so we have to add them all up. We have this 0.146. We have 14.5. And we have, from our first step, was 3.52. $18.17, this is in kilojoules. Did I? Maybe we did this very exact. This one. Usually the phase change is a little high. Because our unit was in kilojoules to start with for vaporization. This is also for acetone, so that's why it's kind of a little bit different. You did it for what? Okay. So it would have been fine. Okay, I think the problem was these were in joules per mole Kelvin, and when I made the answers, I used grams instead. I made a mistake. So we were supposed to, so when you did it with just using grams, you got the right answer, which is actually my mistake answer. Because of these are in moles. So what should have been A for this is actually supposed to be this 18.17. Okay. So we make a note. Look at units for constants. It's my note for me, also for you. So look at units for constants because that's what happens. My bad. So I accidentally found the answer if these specific heats were in grams, but they're not in grams, they're in moles. So this should be in the answer, this 18.17 kilojoules. So we'll just make a note. We'll edit that. It'll be okay. We're fine. I fell for my own trick. But do we have questions on number 4? Yeah. Last number I wrote. This stuff? Yeah. So that was from the first step. So our first step was that 3.52, going from liquid to boiling. And then this one was from phase change, so boiling. And then this one was from that gas to, or boiling to our final. So when the way we did it here is the actual correct way, looking at the units. The way I calculated the answer is the wrong way, assuming grams. We don't assume grams. We look at our units. Yeah, so our first one that we solved for, we used the C of liquid. It was in joules per mole Kelvin, so we had to use moles here. We use our specific heat. We use our change in temperature. We can convert to Kelvin if we need. And then we get our answer that was 3.52 in kilojoules. Will be converted. Our second one, we did Q equals N delta H. Used our moles. Our delta H, we got our kilojoules, because it was in kilojoules per mole. Third one, we had going up to our final temperature. We used our moles still. We used our specific heat for vapor. Found the change. Got it in joules, converted to kilojoules. Added them all together. Yeah, so we just changed that answer to the correct answer, which is that 18.17. Or 18.2 if we want to keep with the 3 sig figs. Look at units for constants. Okay. Do we have other questions on 4? Are we okay? We're good. We're good. See some thumbs up. We good. Okay. So we'll go to chapter 12. Okay. And we have a question on which molecule will be the least soluble in water. So in order to answer this question, we need to know a little bit about water. So we know water, H2O. We draw the Lewis structure for this. We'll get this bent shape. We'll have these lone pairs. It'll be bent. We'll have these polar bonds. This is polar. That has a net dipole moment, an overall net dipole moment. So this is polar. So we have dipole-dipole because it's polar, and we also have hydrogen bonding because of the OH interactions to make this side by side. So if we're looking for something that's the least soluble in water, we want something that doesn't share these interactions with water. We want something, probably the least would be something that's nonpolar, something that doesn't have dipole-dipole or hydrogen bonding, because also this has dispersion, but that would be the weakest interaction it has. So something that's the least soluble in water will have 1 of 3 rather than 3 of 3 interactions that are the same. So we're looking for something with dispersion, something nonpolar. And just from looking at my answer choices, I see that we actually have multiple answers for this question that I did not put on my answer sheet. Yay, okay. I'm great, okay. So we look at A, we actually have multiple choices, so let's change this to check all that apply. Yeah, no, it happens. You can tell I made these questions. You're welcome. A is CCl4. So we draw the Lewis structure for that. We're going to have carbon with 4 chlorines attached. And each of those chlorines are going to have those lone pairs. So many dots. Okay. So we're going to have polar bonds between the carbon and the chlorines. All of them. They're all going to have the same strength, the same pull. They're all pulling away from carbon in all directions. So there's no net dipole force because they're all pulling the same strength, all different directions. The electrons aren't being pulled to one side versus the other. We don't have a dipole effect. So because of that, although we have polar bonds, this is a nonpolar molecule. So it's nonpolar. If it's nonpolar, it has dispersion forces only. So this is one of the type of things we're looking for. But there may be more, so we'll look at the other choices. B says we have CH2Cl2. So if we draw that, we have carbon with 2 H's. And then we have chlorine attached to those carbons. And chlorine is each going to have those lone pairs. We're again going to have those polar bonds, pulling electrons away from carbon because chlorine is a more electronegative element. In this case, we do have a net dipole force. It's pulling away from carbon, away from the hydrogens. Because we have this net dipole moment, we have a polar molecule. Because polar molecule, we have dipole-dipole interactions, as well as dispersion. So far, A is better than B. B would have 2 things in common with water. A only has 1. We want to know what's least soluble, so less likely to dissolve and interact with water. So then we look at C. C has OH, CH2, CH2OH. So we have oxygen bonded to a hydrogen, bonded to a C, bonded to two H's, bonded to a C, bonded to two H's, with an oxygen bonded to a hydrogen. So these are like written how they're supposed to be drawn. Kind of gives you a hint how to draw them. This is also supposed to have a bent shape. So we have pulling of electrons toward oxygen, away from hydrogen, away from carbon. So we have a polar molecule. We have polar bonds, and we have net dipole moments. So we have a polar molecule. So we have dispersion, we have dipole-dipole, because it's a polar molecule. Also, we have OH bonds, so we have oxygens bonded to hydrogens directly. So we have hydrogen bonding as well. So this shares 3 of 3 interactions with water, so this will actually be most soluble compared to the other 3. So A so far is a good one. Only had dispersion. This one, not good one, not good one. We'll look at D. D is CO2. We drew this one before. We had carbon with double bonds to oxygen on both sides and lone pairs. This one had polar bonds, but the polar bonds canceled because they're going in opposite directions. This molecule is linear. So it's kind of like tug of war, but they're pulling equally. So there's no net dipole, so this is nonpolar as well. With a nonpolar molecule, we have dispersion. So we kind of have a battle between A and D. CL4. So I think when you're looking for, oh yeah, okay. Maybe Technical Apply wasn't actually the one we needed. Maybe I was good to beforehand. Because we're looking for least soluble in water, so solubility is going to have to do with not just interactions, but also size and shape. So when we had CCl4, where I was going with this? Yeah, I think from our knowledge, we were looking for least soluble. These both would be least soluble. Yeah, let's just go with, yeah, because they're both nonpolar interactions. We both just have dispersion. So I should have probably made something nonpolar. I think I forgot about CO2 canceling out. So actually, A and D would be the good ones for this, for least soluble in water, based on intermolecular forces. So we're looking for like dissolved like. So C would be most like water because it has hydrogen bonding. B would be close to water because it's nonpolar. Oh no, it's polar. It has dipole-dipole interactions. A and D are going to have nonpolar interactions. They're least soluble in water. I was thinking maybe like you can base it off of molar mass, I think, after looking at nonpolar interactions, but I don't think they really talked about that in the chapter. So we'll go with A and D because they're both nonpolar interactions. They only have dispersion. That's the only thing they have in common with water. But do we have questions on solubility? Something being soluble in another? Yeah. Actually, if we look at these hydrocarbons, so if we just had like CH4, and we drew that one out, we had C bonded to H's. This would be a molecule where we don't have those arrows, because these the electronegativity between carbon and hydrogen isn't big enough to make a polar bond. There's a chart with like the charges, electronegativity, not the charges. So you kind of have to be familiar with the chart. Usually anything bonded to oxygen, nitrogen, and fluorine that aren't oxygen, nitrogen, and fluorine are gonna make polar bonds. So obviously if oxygen is bonded to oxygen, that's not gonna be a polar bond. They're pulling with the same strength. They have the same electronegativity. Yeah, so the first step to being polar is you need polar bonds. This one doesn't meet the first step, so we just go nonpolar right away. If we do have polar bonds, like in CCl4, then we say, okay, well, do we have a net dipole? Do we have a net movement of electrons toward one side versus the other of the molecule? In this one, we don't, because we have the same molecule all around pulling with equal force to take those electrons away from carbon. So we don't have one side of the molecule more positive or more negative than the other. Usually. Like if you look at the electronegativity chart that's in your book, it shows you like the different values. And I think I noticed that pretty much the difference between oxygen and nitrogen is that 0.5, which you need 0.5 or higher to be polar. And the difference between nitrogen and fluorine is also 0.5, and oxygen and carbon is probably over 0.5. So like those would be polar from what I saw. So it'd be good to like kind of memorize some of them, not the numbers, but generally like, okay, if I see this in a molecule bonded to not itself, it's probably going to be polar, something like that. And knowing that carbon hydrogen is not polar is a good key one to remember as well. Yeah. Wait, what? Move it over. Down. I don't know what you want to see. Okay. I guess you're looking for like B, maybe? Okay. I wasn't sure. That's why I'm like, which way am I moving this to show you? Okay. Do we have other questions? Are we okay? Intermolecular forces, solubility, yeah. Does anyone remember the trend for electronegativity on the periodic table? Yeah. Fluorine is most electronegative, so we don't really like count the not the halogens, the noble gases. So it's going to be to the right and up is going to be the most electronegative. So the further the left you get, the least electronegative you're going to get. So hydrogen is low electronegativity, yeah. Good question. Other questions? We okay? We're good. We're good. Okay. So, next question. We have question number 6. Says silver nitrate has a lattice of negative 820 kilojoules per mole and a heat of solution of positive 22.6 kilojoules per mole. And we want to know what the heat of hydration is, and we also want to know if the heat of hydration is endothermic or exothermic. So for endothermic and exothermic, are we going to have a delta H that's positive or negative? So for endothermic, are we positive or negative for delta H? Positive. So positive delta H is endo. Negative delta H will be exo. So right off the bat, we can kind of see if we match up. So negative and endo, we can just cross that out. Positive and exo, we can cross that out. Positive endo, that's okay. Negative exo, negative exo. So right now we're just looking at A, B, C for this answer choice. So we want to know our equations for lattice and solution and solvent. So let's look at our equations. So we're going to have to remember those equations. We have our heat of solution, so the very general one. Heat of solution is heat of solute. So breaking up those solute-solute interactions, also breaking up the solvent-solvent interactions, and then forming those solute-solvent interactions, which is the mixture. So the overall reaction is this. we're talking about lattice and heat of hydration. So if we have heat of hydration, we have an ionic compound in solution. So when we're looking with heat of hydration, we're working with an ionic compound in water. So our solvent and mixture are going to come together and create that heat of hydration. Okay. Okay, we also have heat of solutes. So if we're given lattice though, and lattice is negative, or heat of solutes is negative lattice. So if we can plug in negative heat of lattice here to get our equation of heat of solution. So heat of solute equals negative heat of lattice. So those are equations we want to work with. So heat of solute is negative lattice, so we put negative lattice in. Our solvent and our mixture create heat of hydration because we're working with an ionic compound in water. Specifically, we're working with silver nitrate and water. So we can find heat of hydration, so we're looking for this. So we're given lattice is negative 820. So we have a negative 820. This is in kilojoules per mole. Plus what we're trying to find. And that's going to be equal to heat of solution, and we're given a solution is positive 22.6. So this is going to make a positive 820. Hydration. So if we subtract that, we're going to get a negative number for our answer, so we can cross out that positive number. And we're going to get a bigger negative number, so we can we don't even really have to do the calculation. We can look at our answer choices and see that it's going to be B. We can also do the calculation if you would like. Cross out the positive because we had a positive equals a positive plus. I crossed out C, D, and E because the negative was with endothermic, and we said negative is exo. The positive was with exo, and positive is supposed to be endo, and then the positive was with, positive with endo. Ooh, I don't know why I did that, sorry. Okay, sorry. So D and E was crossed out because they didn't match this positive with endothermic, negative with exothermic. C I crossed out because I saw that we're going to get a negative answer for our problem. And then we could pick B because this is going to be a very big negative, not that very small negative. Or we can do the calculation if we'd like. Okay. So we have questions on 6, on hydration, on heat of solution, endothermic, exothermic. We good? We're good. Cool. So then we can look at 7. 7 says, when dissolved in water, which of the following would produce the highest vapor pressure? And I'm going to pull this over. We're going to our answer choices. When dissolved in water, which of the following would produce the highest vapor pressure? So vapor pressure, that equation is looking at Raoult's law. So that was P of solution, or the pressure of solution, equals the mole fraction of the solvent and times the pressure of the pure solvent. So we're looking at these different compounds and how they're pretty much affecting that mole fraction. So the mole fraction of the solvent equals the moles of the solvent over total moles of solvent and solute together. So the more moles of solutes or of solution that we have, the smaller that mole fraction is going to be. And the smaller that mole fraction is, the lower the vapor pressure is going to be. So the more particles you have in your solution, the lower the vapor pressure. So you're depressing the vapor pressure the more stuff you put in your water. So we're looking at which of these is going to give us, we're looking for highest vapor pressure. So which one is going to depress the vapor pressure the least? So which one has the least amount of particles? Because the more particles, the lower the mole fraction, the lower the mole fraction, the lower the vapor pressure. So we're looking for the one with the least amount of particles. So if we look at our choices, we have calcium carbonate. That's a metal and a polyatomic ion. So this is ionic. If it's ionic, it's an electrolyte. It's going to break up in water. And what's our Van Hoff factor going to be for this if we guesstimate? It's going to be the 2, because we're going to have calcium 2+ and carbonate 2-. So our Van Hoff factor is 2 for A. So that means for every mole of calcium carbonate we put in, we're going to get 2 moles of stuff out. Okay. So we're going to want to compare that to our others. So our calcium carbonate is ionic. That means it's an electrolyte, or, well, it will be an electrolyte. We have a Van Hoff factor roughly 2. If we guesstimate it, because calcium carbonate is going to break up into calcium and CO3 2-. So we have Van Hoff of 2. And we're looking for what's going to have the least number of particles. So kind of like the lowest Van Hoff we're looking for, because the least amount of particles is going to give us the highest vapor pressure. Highest overall would be if we had no particles, but we're going to look for the least amount. We're assuming we're putting the same amount of stuff in as everything else. So we're assuming if we put 1 mole of this, 1 mole of this, 1 mole of this, compared to the others, which one will give us the highest. So the other one is potassium sulfate. This is also a metal and non-metal, so this is also ionic. So it's also an electrolyte. So what's the Van Hoff factor going to be for this one? 3, because we have 2 potassiums and 1 sulfate for every potassium sulfate molecule. So that one's higher, so far A looks like the better one. But we'll keep going. C is aluminum sulfite. So that's also ionic. What's our Van Hoff factor for C? It's going to be 3, because we're going to have that sulfite and we're going to have 2 aluminum. That's also 3. Then we look at D. D is C6H12O6. So that's going to be glucose. So that's all nonmetals. So it's the non-electrolyte. So its Van Hoff is 1. Okay. E is also going to be made up of nonpolar things. It's going to be a non-electrolyte. And its Van Hoff is 1. So our answer choice is between D and E. Which is the highest vapor pressure. If we're looking at, Okay, so the problem with this question is I should have given you masses of them. So if I gave you 1 gram of everything, then we could solve this problem. Versus if I gave you 1 mole of everything. If everything's 1 mole, then D and E would give you the same type of vapor pressure, because the mole fraction is moles of solvent over total moles. If I give you it in grams, let's say I actually put grams in here instead, we would still have our choice between D and E. But if we had grams, how would that change our mole fraction between the glucose and the CO2? Which one will give us a higher mole fraction? The one with the higher molar mass or the one with the less molar mass? The higher. Or the less, let's see. Okay, so if you have a higher molar mass and you have 1 gram of it, you're going to have less moles. Versus if you have a lower mass and you have 1 gram of it. So the higher molar mass gives you less moles of molecules, per gram. So that's going to give you that larger mole fraction. So if we converted these to grams, converted these to moles, we would have a smaller mole for our glucose, which would give us that higher vapor pressure. So what this one is, if one convert to moles, the higher the molar mass, the less moles you get. So for this one, if they just gave us glucose and CO2, we can't tell the difference if it's just 1 mole of each. But if we give it to us in grams, then we can tell the difference. It's going to be the one with the higher molar mass, because the one with the higher molar mass is going to have less particles. Because the grams per mole, we need more grams to make a mole of things. So if we did it based on mass, it would be D, which I think I did for the answer choices. I think I did it based on mass. So I should have given you mass for this type of problem on 7. Or made it E. Why did I make it E? Yeah, and we're looking for the highest one. E1, because you get less particles though. Because like if we look at the molar mass, E would be the lower mass, yeah. E would be a lower molar mass. So if we have 1 gram of it, we convert that to moles, we're going to get more moles compared to the one with the higher molar mass. Because the higher molar mass gives you, requires more grams to create a mole. So I made the key wrong. Yeah, it should be D based on mass. So if all of them were 1 mole, then the answer would be both D and E. If you're given in grams, you go with the one with the higher molar mass because that's going to give you the least amount of moles. Yeah, if it doesn't give you a molar mass, you assume the same. But I don't think she's going to give you a question, or on the ACS there will be a question where it will be ambiguous. She'll check it a little bit more. I was trying to make these quick. My bad. But yeah, I think I was originally making it based on molar mass, and it should have been D for that, because the one with the greater molar mass is going to give you least amount of moles with the same mass. Like if you have 1 gram versus 1 gram, when you convert that to moles, you're going to get less moles for the one with the higher molar mass. Okay, so that one should be D. Do we have other questions on vapor pressure? Yeah. Vapor pressure and intermolecular forces. It depends. So if you're looking at yeah, I think with this one, I shouldn't have given you CO2 because that's in gas form, and Raoult's law is looking at solid in liquid. So my E answer is just a really bad E answer, and I should have given you a different choice for E. Because for Raoult's law, looking at solid in liquid, that's the difference between looking at intermolecular forces and looking at Van Hoff. So Van Hoff kind of looks at intermolecular forces because you're going to have a higher Van Hoff for things that are ionic versus things that are non-ionic or non-electrolytes. But if you're looking at like liquid in liquid, that's when you look at intermolecular forces, because Raoult's law is only for solid and liquid. Or if you're looking for gas and liquid, which I put here, which I shouldn't have put here, I think that's actually Henry's law. So my CO2 answer was a bad answer to put in this other question. how many particles you're going to make versus that one particle. Oh, in the equation, you're going to it's going to affect the mole fraction.
So is it like mole fraction equals whatever?
Oh, it's going to be mole fraction equals, we have moles of solvent over total moles. So total moles will be solvent and solutes. In the moles of solutes, you're going to have however many moles times Van Hoff. Because say we had potassium sulfate. We had a Van Hoff of 3. So that means for every mole of potassium sulfate, we're going to get 3 times as many moles of particles. Van Hoff factor is used for things that are going to affect number of particles versus the actual substance you're mixing in. So for all of your colligative properties, you're going to have Van Hoff factors. So you're going to have to realize if you're working with electrolyte versus a non-electrolyte. What do you mean? For this one's for Raoult's law. This is pH solution. You also use it in Henry's law with, I think, is for gas in solution. You also use it for freezing point depression, boiling point elevation, osmotic pressure. So all of those colligative properties are going to have Van Hoff. Yeah. Other questions? Are you okay? Colligative properties? I think we have more colligative properties coming up. So I gave you a bad choice. E is a bad choice. Because this Raoult's law, this highest vapor pressure, should have been just looking at solids and liquid. Okay. So 8. What is the boiling point of an aqueous solution that is 10% sodium carbonate by mass? So for this one, this is kind of looking at mainly converting that percent by mass into what are we going to need to convert that into if we're looking at boiling points? Moles is going to help us. So if we look at this unit, we have degrees Celsius per little m. What is little m? Molality. And how do you find molality? We have moles of solutes over kilograms of our solvent. Okay. So if our solution is, our aqueous solution is 10% sodium carbonate by mass, what is the other 90%? H2O. So we have 10 grams. If we look at like 100 grams as 100%, we can say that we have 10 grams of the sodium carbonate and our 90 grams of H2O. Then we can convert those to moles and kilograms respectively. So our sodium carbonate will be our solutes and our H2O will be our solvents. So if we convert water to kilograms and move the decimal place over 3 times, so we get 0.090 kilograms. And then we need the molar mass of sodium carbonate to get that one. So we have 3 times 16. We have 1 times 12, and then we have 2 times sodium. I don't remember what the molar mass of sodium is. Does anyone have that periodic table to check? Okay, so 23 we can say. So we have 46, we have 3, 42. No, it's 18, sorry. 3 times 6 is 18, 48, plus 12, plus 46, it's 50, 60, 106. Okay, 106 grams per mole. So 1 mole is 10 divided by 106 grams. That'll give us moles. What do we get it? Point what? 0.094. So we get 0.094 moles of our sodium carbonate. divided by our kilograms of solvent, which is our 0.090 kilograms of our water. 1.04 is going to be our molality. If we're looking for boiling points, we can kind of look at our KB for help with that. So our KB is in degrees Celsius per molality. Our boiling point is in degrees Celsius. So our change in our boiling point is going to be that KB times that molality. So we can get degrees Celsius. This is a colligative property, so it depends on the amount of particles you have. Because molality is in solutes over solvents, we can just multiply the Van Hoff factor in. So we multiply by I. What is I for this if we have Na2CO3? It's going to be 3, so our I is 3. So we can plug in our numbers to find the change in temperature. Our KB was 0.512 degrees Celsius per molality, or per molal. We found molality as 1.04, and our Van Hoff factor is 3. So if we multiply those out, we'll get the change in temperature for our boiling point. What's our change in temperature for boiling if we multiply those out? 1 times about 1.5-ish. 1.59? Okay. 1.59. I'll keep it at 1.59 or 1.6. Maybe we'll round to 1.6 because I think the numbers over here are rounded to 1.6. What's the boiling point of working with the solvent is water because it's aqueous. So what's the boiling point of water? 100. So we're elevating the boiling point, so we just add this to 100. So we get the final, so we have 101.6. So we look at that, and I should have put units. So I'll put them in now. So 101.6 is going to be A. So the big thing there was solving for molality using percent mass. Yes. Yeah, when it's freezing, because we work with boiling point elevation. So whatever change in boiling point you get, it's going to be higher than your initial. And we have freezing point depression. So whatever freezing point you start with, you should get a lower one when you end with. So you can subtract it from your freezing point if you have freezing point. So if we were looking at our answer choices right off the bat, we could have just picked out E as wrong because it was below 100, and we're looking at the boiling point of water when we add stuff in. So we should elevate the boiling point, not depress it. Okay. Are we okay with number 8? Are we okay converting between percent mass and molality, and then how to use Van Hoff, when to use Van Hoff? Okay, thank you. So look at the next one. We have 9. An aqueous solution is 8.6 sodium chloride by mass, and we want to know what the molar concentration is. So what is molar concentration? What's that unit? Gives you a hint. Molarity, and how do you find molarity? You got moles of solutes over your liters of solution. Okay, so we're going to, it doesn't say here, but we're going to assume that the only thing really taking up volume is going to be the water in the solution and not really this NaCl when we work with this. So we have 8.6% NaCl by mass. So we can say that we have 8.6 grams of NaCl. And then what would be the other 91.4 grams? That would be water. Okay. So we have to go from grams to moles. So we have the 23 and 35.45 because we need a molar mass of sodium chloride. So that's about 58.45. So 1 mole, 58.45 grams. What time do we have? Ooh, dang. And we get moles of that, and then we also need to go to grams to liters. So our understood or our assumed density of water is 1 gram per milliliter, or 1 gram is 1 milliliter. So we can say 1 milliliter is 1 gram. And then if we go from milliliters to liters, we have 1,000 milliliters in a liter. So I get that one. So we pretty much move this one over 3 times. 0.914 liters. And then what do we get for our molar mass when you do 8.6 divided by 58.45? 0.147. Thank you. Here's a mole, so we do the 0.147 divided by the 0.0914, and that should give us our molality, or molarity, sorry. So I think the 6.21 is a little big, so that one's not it. What was our answer? Our answer was supposed to be E, yeah, that 1.61. So we should get that number. Okay. Do we have questions converting from percent mass to molarity? Are we okay with that? Okay, we good, we good. Okay. So we'll look at the next one. So we're looking at chapter 13 stuff. We have consider the following reaction in the data below. We also have more answer choices. And we want to know what the reaction, the order of the reaction is in terms of just the NO2. It's not the overall order, just the order of NO2. So we can just focus on NO2. We can compare what will kind of drop out F2, because we're looking at NO2 and F2. We can't just use the coefficients in our overall reaction, because we can't do that. We can only use the coefficients if we're given the mechanism when we're looking at order and kinetics. So we can't just say it's second, because it's not. So we're going to look at our data, and we have the first one, these two, will give us the same number for F2, so that will kind of cross out, and we have different numbers for NO2. We want to look at NO2 for the order, so we just want to focus on that one. We have, so our whole rate law should be rate equals some K times our NO2 to an order times our F2 to an order. We just want to find N. We just want to find the order of NO2 versus the others. So we're going to kind of compare 2 different rate laws. We're going to find compare the rate law with this rate and these concentrations compared to this rate and these concentrations. I prefer to put the bigger one on top when I divide. So I'm going to put 0.051 over 0.026. And that will be equal to the 0.2 over the 0.1 to some number. So we have about 2 equals, I think that's also going to be 2. So 2 to what number gives us 2? Is 1. So we have N is 1 for this one, for NO2. And we're only looking for the order of NO2, so we can stop there. So it's first order in terms of NO2. If it asks for overall, then we'd have to solve for when NO2 is constant and look at what the F2 would give us. But we don't have to do this for this problem. We can just look at NO2. So it's first order, it's not second order. We're not looking at that coefficient saying it's 2 and it's second order. So we can't do that with an overall reaction. So we have questions with finding order with the rate law. We're good. Okay. So look at the next one. It says, for the decomposition of SO2Cl2, a plot of the natural log of SO2Cl2 versus time is going to yield a straight line with a slope of negative 1.42 times 10 to the negative 4 at a certain temperature. And we want to say, if the initial concentration is 0.15, what is going to be our final one after 2 minutes? We're going to assume constant temperature here. So if we're looking at a plot of the natural log versus time, and we get a straight line, what kind of order is that going to be? It's going to be first order. Our zero order will be just concentration versus time, I think. She might, I'm not sure. That would have been a good question to ask her ahead of time. But I think if she gives you it on the test usually, then you can kind of assume it'll be on the final, but I'm not sure. And for the ACS, I don't think they do that. Because first order is going to, when we look at the graph of first order, so if we graphed 1 over concentration versus time, that would give us second. If we did concentration versus time, that gives us first. It has to do with the integrated rate laws. So when we have ln of the concentration equals negative kT plus ln concentration of O, this is kind of the reaction that we have, and we have ln of A versus time. So it's one of those, or negative say, sorry. We're actually going to get a negative slope, not a positive slope because of this. So it has to do with the characteristics of a first order reaction where you plot the concentrations versus time and it gives you a weird slope, so then you have to kind of say, okay, well, what if I do this to the equation, what if I do that, and then see what order you have. So it's one of those characteristics that you kind of have to remember. So this is first order. Second order would have been 1 over the concentration, so the inverse of it. And I think first order is just the concentration with time. 0 is just concentration in time, so by itself, plain. First order is natural log, and then second order is the inverse, the 1 over. Okay. If the slope is negative 1.42 times 10 to the negative 4, what is our K value? It's going to be the opposite of that because our equation is negative KT. So our slope is negative K. So our K should be 1.42 times 10 to the negative 4. It's in inverse seconds, so per second. We want to know what the initial concentration, we have initial concentration, so we're going to use this equation. Have initial, we are given a time, we know K because of that slope, and we're being asked to find what the final will be. So we have to use this equation. When we use this equation, we're going to plug in our values. We can't plug in all our values as is because the K is in seconds or per second, and our time is in minutes. So we have to convert to minutes for that one. So if we look at our equation, we have ln of A equals negative KT plus ln of our initial. Yeah, it is definitely easier to convert the 2 minutes to seconds versus the per second to per minutes. Yeah, so that's what we're going to do. So 2 minutes is how many seconds? 120, so we're going to use 120 seconds as t. Our ln of AT, so we're trying to find AT. So we'll keep that the same for now. Try to find that. We have negative or K, 1.42. Oops. 10 to the negative 4. Then we add the ln, times our t, our 120. Times our 120. So it's negative KT. Plus the natural log of our initial. So our initial is that 0.15. The slope is negative for this one because it's a negative KT. Oh, on the graph. On the graph, like this is a negative slope versus the other one that I drew was a positive slope, so that didn't match what this order. It was just for what the graph should look like in case they give you graph instead of saying this has the slope of this value, and they just give you graph. Yeah. The slope is negative K, so K is a positive number. We're given slope as negative. Slope is just negative K. So K is the positive version of that. So we plug K back in, we're gonna get a negative. Yeah, so when it says slope, we can pretty much put slope in for this whole value. Because this is in y equals mx plus b form. So x is just t, the m is negative k. So that's why we just keep a negative there, because k is the positive value, but the whole equation has a negative k in it, which is slope. So we can just put our slope value in, or we put our k value in and keep the negative from the equation. So the negative is part of the equation. That's why we keep it. Good question, though. So if our initial is 0.15, our SO2-Cl2 is a reactant, do we expect our concentration to get bigger or smaller? We expect it to get smaller. So pretty much anything over this number is not a good number to have. So in scientific notation, this would be like 1.5 times 10 to the negative 1. So, or no, yeah. Actually, we don't have anything to just cross out. Cool. Okay, interesting. But so we'd have to figure this one out. So if we solve this, so we'll have to do the negative 1.42 times 10 to the negative 4. We'll multiply that by 120. Then we add it to the natural log of 0.15. How do we undo a natural log to get the concentration by itself? We have to do e to this. So we do e to both sides. So whatever we get for this is going to be our exponent for e. Okay, so our concentration should be whatever e to that is. I think for this one, our answer should be a. So we should get 1.47 times 10 to the negative 2. Right, 11 is a. We didn't get that? The negative first? Okay, so we put a negative 1.42 times 10 to the negative 4. We put times 120. We add it to ln, not the log, just the natural log of 0.15. Okay. We got to the negative 1.47 times 10 to the negative, okay. Okay. So we got, what did we get for our answer then? 0.147. Okay. So if we convert that, 1.47 times 10 to the negative 1. Okay. So then we have to change our answer. Okay. Sorry for the amount of errors in this answer choices. My bad. That's why we go over them together. Try to figure those out. What time is it so far? We're okay. We got time. Okay. So number 12, or do we have questions on order reaction or using those equations? Yes? No? Yes. Yes, because the slope, we were talking about the decomposition of SO2-Cl2, and it gives us a plot of ln of SO2-Cl2 versus time, and that gives us a straight line, so that tells us we're using second order. And that's why we use that equation. Okay, so we have to know those kind of interactions between concentration and time and what's going to give us a first order, second order, zero order reaction. So, more stuff to know. Okay. With this one, we have a mechanism. We have to find the rate law. So when we're given a mechanism, do we base it off of the slow step or the fast step? Slow step. So we don't even look at the fast one. We just look at the slow one. It's the first one. So that's good. When we write a rate law, do we put reactants or products or reactants and products? Just reactants, so we don't even look at the second half of this equation. We're just looking at the A, B, and B. Do we multiply our reactants or add them? Multiply. Also, all of our answer choices have them multiplied, so we're good. First reaction has K1 in it, so anything with K2 can go away. And we're looking for K1 times AB times B. That should be E for our rate law. Okay. Not too bad, not too bad. Because our rate should be K, or specifically this K, times our reactant times our other reactant for our slow step. Number 13 is a little bit more involved. So our slow step is the second one. If we write our rate law, it will look like our rate times our K2 times our reactant, so we don't look at products, H2 times N2O2. So that would be our preliminary rate law, but we have a problem with it because in our first step we made N2O2 and now we're using it. So what's that called when we make something and then use it in the next step? Not just spectators usually like they're at the beginning, they're at the end. Those are like spectator ions when we have one reaction, but now we have a step-by-step reaction, so it's a little bit different. Intermediate. So these are things that we don't see in our overall reaction. They're going to cross out. We make them just to use them up. So intermediates, can they be in our rate law? No, we can't have intermediates in our rate law. What about catalysts? Can we have catalysts in our rate law? Yes, we can, because they affect our rate. They're going to speed up our reaction. So catalysts are fine. So the ones that you find in the beginning and the end. Do we have any catalysts in here? We have beginning and no, we don't really. But we have that intermediate, so we make it and we use it, so we have to fix this rate law. Luckily, we have a reversible reaction, so we can fix the rate law. So instead of making it in terms of N2O2, we're going to figure out how to make it in terms of NO. So if we look at our first rate law, we know that the forward is equal to the reverse rate. So if we write the rate of our forward reaction, we have rate equals K1 times our NO. And now we can use the coefficients as the order because we're working with a mechanism. So the rate of the forward is our rate times K1 times NO squared. Our rate of our reverse is K inverse 1 times N2O2. Because it's in equilibrium, our rate of forward is the rate of reverse, so these rates are the same. So we can set these equations equal to each other. So K1 times NO squared equals K negative 1 times N2O2. We want to solve for N2O2 so we can substitute it in. So if we solve for N2O2, we're going to get a K1 over inverse K times our NO squared. So we can plug this in for N2O2 and we can get our answer for that. When we look at our answer, look at our answer choices. These are answer choices. Let's look at, so if we plug this in, let's say this was our original rate law with our intermediate. And now I'm going to substitute what that intermediate is in terms of a reactant instead. And that intermediate was NO2 squared and then K1 over inverse K. So what is a constant divided by constant multiplied by another constant? We're going to get a constant, some constants. So these K's are going to combine into a super K. And we're going to have H2 times NO2 squared. And then we look at which one matches this. We have C. So for this one, when we're given a mechanism with an intermediate in it, in our slowest step, mechanism with our slowest step, that has an intermediate, we have to go back, see how we can manipulate our equations or our rate law to get us something without an intermediate. If we didn't have that reversible reaction, we couldn't solve this problem. Third equation, so the third equation is also fast. It doesn't help us figure out how to take out our intermediate, so we don't really use it for our rate law. It's important for our overall reaction, but not for creating our rate law, because your rate law is dependent on the slowest step. The answer should have been C. So answer should be C, because we'll have some K times our H2 times our NO squared. We didn't use the third one because it was fast. We used the first one because it was reversible and it had our intermediate in it. So if we reverse that reaction, we're not creating the intermediate gap. How do I get rid of the k squared? We have k1 divided by k negative 1. Oh, not negative 1, but it's k sub 1, so some k. So if I put a number in for k, I'll have like, maybe if k1 is 2, k negative 1 is a different number. They're all different numbers, so you create a new number from that. You can't just like you can't put k squared because the k's aren't the same. They're not the same number. That's why they have different subscripts to denote like different numbers. Yeah. NO2 raised to the 2. If we look at our rates for our reversible reaction, so the forward was NO squared because of the 2 in our coefficient. Where is it? Sorry. My bad. We can, because this is a mechanism. We can't use the coefficients in an overall reaction when we're looking for rate law, but we can use the coefficients in a mechanism. Because we're given step by step to get an overall reaction, we're allowed to use coefficients. Yeah. We choose the slow one because you're only as fast as your slowest reaction. Something like that. It's one of those sayings. So you're only as strong as the weakest link, or you're only as fast as your slowest reaction. Yeah. Because this fast one, so in our slowest one, we have an intermediate. We can't have intermediates in our overall rate law because when we're given just our overall reaction and our rate law, that's not reflected in our overall reaction. It's going to cancel out. We won't see it. So we can't have intermediates in our rate law, and that's why we had to go back to the first step to figure out how can we substitute N2O2 for something else, because N2O2 can't be in our rate law. Sure. Other questions? Okay. We're good. Okay. Oh, okay. Not good. Yeah. Down. Oh, this part when I was just like, so like if I had numbers for these, so if the H2, that's from our original rate law. So our rate law was K2 times H2 times N2O2. We couldn't have N2O2 in there, so we figured out by using our reversible reaction what N2O2 could be, and we plugged it in. We plugged it in to get, we plugged into this equation to get, we plugged this in to here, and then we simplified. Yeah. Yeah. I plugged it in to get a new one. Our K's could be any number. They're usually not the same number, so you can't just put K squared over K or just a K. Yeah. The reversible one. So the fast one that was number 1 and it had the intermediate as its product was reversible, and that's why we could do it. So it had an arrow that was forward and reverse. Where'd it go? Yeah. So we had an arrow that was forward and reverse, and that's why we were able to use it. If we didn't have a reversible reaction, we couldn't have done this problem. Yeah. Number 10, what happened? Number 10. I would have to go back to what we were looking at. Number 10, for this order reaction, we were given a table of data for number 10, and we're asked to find the order. We couldn't use our overall reaction to find the order because we can't do that. We have to have a mechanism to use coefficients as orders, if that's what you're asking when you're asking about number 10. Yeah, so our rate for this one, for this reaction, is some K, some constant, whatever it is, times our NO to some power. We don't know. We have to figure it out experimentally. And then times F2 to some power. We don't know. We had to find it experimentally. K, when we compare these reactions, our K is going to cancel, so we don't have to know our K value for it. Yeah. Okay, sorry. But we got to move on. We have more to do. Okay. So let me look at chapter 14 stuff. What time do we have? We don't have a lot of time. Okay. So chapter 14 stuff, we have use following chemical reaction to answers 14 through 15. So we have this. 14 says, if the reaction is at equilibrium and the volume of the container that it's located in increases by 0.05 liters, which of the following will occur? So if we're increasing our volume, in order to achieve equilibrium again, we're going to want to go toward one side that's going to give us the most amount of gas to fill that volume again. So on our left we have 1 mole of gas, on our right we have 2 moles of gas, so this is going to shift right if we have a volume increase, which we do. So this should shift right. 15 says if a reacting vessel contains a partial pressure of CO2 at 2.5 and a partial pressure of CO at 0.5, which way are we going to shift? We're given a Kp, so we can calculate Q and compare. So Q is going to be equal to our products over reactants power of coefficients. So P of CO squared over our P of CO2. We don't include carbon because it's solid. We don't put that in our equilibrium constant. So we solve for Q. Q will be our 0.5 squared divided by 2.5. And that should be, I think it's bigger than Q. So K is, so what do we get for Q? Does anyone want to calculate that for us? So 0.5 squared and then divided by 2.5. 0.1. And 0.1 is bigger than the 1.2 times 10 to the negative 3. So K is less than Q. If K is less than Q, which way are we shifting? Shifting left. So for this one, we have to calculate Q compared to K. This is our Kp. Yep, if K is if less than Q, then we always shift left. If K is greater than Q, we're going to shift right. Because if K is less than Q and Q is bigger, that means Q has more products. And if we have more products, we're going to be shifting toward the left to make more reactants again. Okay. Do we have questions on Le Chatelier or K and Q? You okay? We're good. We're good. Okay. Then we have 16. What is the molar solubility of barium fluoride in pure water? Actually, because of time, we're going to skip that one and we're going to go to 17 because 17 is the vamped up version of that. So we have the solubility of magnesium hydroxide with a pH of 10. So not just in pure water, it has a pH. We'll go to this one. So we look at magnesium hydroxide and how it's going to break up. It's going to break up into magnesium 2+ and hydroxide, 2 of them. If we have a pH of 10, that means we have a pOH equal to 4. If we have a pOH equal to 4, that means we have a hydroxide concentration of 10 to the negative 4. Because pH plus pOH equals 14. And pOH equals the negative log of the hydroxide concentration. So our hydroxide concentration at pH 10 is 10 to the negative 4. So when we do our table, we don't look at solids, we only look at aqueous, and we have an initial for our hydroxide. Plus X. Or S, because we're looking for solubility. S because we have a 2. So when we solve, we'll have our KSP equals our products over reactants power coefficients. We can't put any solids in, so we have magnesium 2+ times hydroxide squared. So our KSP is given. KSP is given. Set that equal to our magnesium is just S. And then our hydroxide is 10 to the negative 4 plus 2S. And we're going to assume that S is small, so we're only going to put the 10 to the negative 4 in. So we're not going to put the change in S. That's the approximation, and we're still going to square it though. So then S is going to be equal to 2.06 times 10 to the negative 13 divided by 10 to the negative 8. Should give us, should be the same 2.06, but negative 13 plus 8 is 9, 10, 11, 12, 13, 5. So we had our plus S gives us S. We have 10 to the negative 4 plus 2S. We're going to do the approximation where we don't count the change in X. So we just put 10 to the negative 4 squared times our S is our KSP. We solved for S, so we divided by 10 to the negative 4 squared, which is 10 to the negative 8. And this should give us 2.06 times 10 to the negative 5, which is B. Yeah. Point 1, yes. K is something times 10 to the negative 3rd, so if you move the decimal place over 3 times, it should give us a smaller number than K. Q is greater than K. Yes. And I think it did move to the right for that one, right? Q is greater than K. That means K is less than Q. It moves to the left. Yeah, it should be, yeah, it's moved to the left. Because K is the smaller number, so that means Q is bigger. Q is products over reactants. Q has more products. If you have more products, you have to move toward reactants to reinstate equilibrium. Okay. Do you have questions on KSP? So for the other one, it's like this one, but we don't have a pH. It's just plain water, so we wouldn't have any initials. Okay. We look at. We have some time left. Okay. We'll look at some stuff from question 15. This one has, which of the following will form the strongest conjugate base? So the strongest conjugate base is going to be the one that has is the weakest acid. So the weakest acid is going to give us the strongest conjugate base. So we're only given acids here, so we're looking for strongest conjugate base. That means weakest acid. HBr is a strong acid, so we can just get that one out. And as you add oxygens, you get more polar and you get stronger. So B would be our weakest one. So that has to do with that trend where you add more and more oxygens, you get a stronger acid. We're looking for the weakest acid, so HBrO would be our weakest one. HBr like plain, is non-oxy acid, so it's just a strong acid. So that one wouldn't be our answer. So we're looking for the weakest acid because we're looking for the strongest conjugate base. So those are inversely proportional. Okay. We'll do a few more of these, and I don't think we're going to be able to finish our review. That'll be okay. So we'll do one of these. We'll find POH or pH. Let's find, so POH from a strong acid, we have strontium hydroxide, so that's SrOH2. So the big part here is that we're going to multiply our hydroxide ion concentration by 2. Because we have 2 moles of hydroxide per 1 strontium hydroxide, we're going to get that 0.01. That's hydroxide. So to find POH, we're just going to take the negative log of that. And so we should get something that is on the lower end because we're looking at POH, not pH. So 11.2 and 12 are automatically out. For this problem, for 19, the answer should be A. which makes sense because this is 0.01 is 10 to the negative 2. So if we take the negative log of that, it should be 2. Yeah, this is the hydroxide ion concentration. We're finding POH. We take the negative log of hydroxide to find POH. When we have pH for 20, we have ammonium chloride, which is ammonium and chloride. This is the actual acid part, weak acid. So to find the pH of a weak acid, we had that shortcut of x squared over our concentration equal to our Ka. We have Kb, so Ka times Kb equals Kw. So Ka times 1.8 times 10 to the negative 5 equals 1 times 10 to the negative 14. So in order to do this, we have to calculate Ka, multiply by 0.01, and then take the square root of that. If we do those calculations, we should get, for number 20C, which makes sense because we're working with a weak acid, so anything over 7 is not good. So we had a choice between C and D. So if you find Ka from Kb, that's given, and solve, we should get C. An ice table, you could do an ice table, but for a weak acid, this is always going to be the approximation. So we usually skip the ice table for that. We have we'll do maybe one more question. Yeah, it looks like we're not going to be able to get to the other ones because we're at 11:51 right now. So our answers are on the end of the review. The review can be found at, thank you. The review can be found at sites.google.com/site/study union. It's the Chem 2046 review. I think I even put this date and time to help you figure out which one it is. So this date is the 4/24, yes, 4/24. Yep, 4/24. My name is Stephanie, so it should have Stephanie on it as well. That's how you will find it. It should be under the spring 2016 reviews, so you'll find it there. Don't forget to please take the survey, either using the QR code or the link. So the QR code and the link is located on the tables, so that's what they look like, QR code and link. I'll put the other link back up.
How many questions?
There are 30 questions in all. We got through 20, so there's 10 more questions that we did not get through. But this is the site where you can find the review. And I'll also post maybe solutions with the updated information for the problems that had the wrong answer choices. I'll update that. And then if you have last minute questions, you can ask me up here. But other than that, good luck with your finals.
Thank you.
Have a good day. There's also like 2 more reviews later in the week for ACS, so if you want to go to those, you're welcome to do that as well. They're also going to be live streamed and recorded.
So will it be more tailored to the ACS?
Yeah, probably. Yeah.
Yeah,